Hello, this is Dr. Joyce Miller, and I'm going over part 2 for the lab activity 4.1, and I want to make sure I said the right date, that this is due November 7th at 4:30. It's a Thursday. So hopefully you've already viewed part 1, and this is part 2, so this is number 4 on page 102, so it has 4 parts to it. So a student measures 25.22 milliliters of CO2 when 85.6 milligrams of sodium bicarbonate reacts with an excess of 1.0 molar acetic acid. Calculate the theoretical number of moles that should be produced from the mass of sodium bicarbonate. So the mass of sodium bicarbonate is our limiting reactant because we have an excess of this, so we don't have to worry about the concentration of this. And for this part of the problem, we don't have to worry about this because this is the experimental amount collected. But it wants to know the theoretical amount that could be collected. So once again, we know it's a 1-to-1 ratio, so we need to convert the sodium bicarbonate, 85.6 milligrams, we need to convert that to grams. So 1,000 milligrams in 1 gram. So that would give us the number of grams, and then we need to use that molar mass. So the grams, we'll go ahead and calculate that, would be 0.0856 grams of our sodium hydrogen carbonate. So 0.0856 grams of our sodium hydrogen carbonate. And how many moles would that be? So we need to convert 1 mole, and our molar mass, you should have calculated that in the previous questions. So that is 84 grams. That's close enough for our purposes. You could have carried it out another sig fig, but 84 is fine. So that tells us the number of moles of sodium hydrogen carbonate, so you can do that math. And then we know for every mole of sodium hydrogen carbonate, we get 1 mole of this and we get 1 mole of that. So 1 mole of CO2 using our molar ratio. So that will give us the number of moles of CO2. So when you carry out this, you'll find that. Okay, now it asks us to use the molar volume the CO2 produced. It didn't tell us, but we're going to continue to use STP because it doesn't tell us any other conditions yet. It will in the next part, but not yet. So we're going to figure STP. So we'll have the moles, so you're going to use PV equals nRT. So you'll plug in the pressure being 1, the volume is our unknown, N will be whatever you calculate here, R will be the gas constant, 0.08206, and temperature will be 273 Kelvin. So you'll solve for V. So you'll rearrange it so that V equals nRT divided by pressure. We're just rearranging, divided both sides by pressure to get it so the volume is by itself. So solve for the molar volume. So you'll have a result there. Now, for the next part, the student records the room temperature as 22.4 degrees Celsius and the room pressure is 74.5 centimeters of mercury. Calculate the experimental value of the gas constant results from the student value. So we're going to plug that in. So now we're going to know a different pressure, and we're going to have the same volume as we solved here, and we're going to have our number of moles, and we're going to have R as our unknown, and we're going to have temperature calculated. So let's reset this up. PV equals nRT, and we're going to solve for R. So we're going to divide both sides by N and by T to get R by itself. So PV over NT gives us R. So we're going to use the pressure So we're going to convert this to atmospheres. So 74.5 centimeters of mercury. We need to change centimeters to millimeters. So there's 10 millimeters in 1 centimeter. So that's going to work out to be 745 millimeters of mercury. That still doesn't tell us an atmosphere, so you need to know your conversion factor for millimeters of mercury to atmospheres. So you convert this to atmospheres. And I'll tell you right now, you should get a value less than 1 when you do that conversion. And so now you need to find T in Kelvin, so you're going to convert 22.4 degrees Celsius and convert to Kelvin. So you've got a new pressure value. You're going to use the volume from part B. You're going to use the N from part A, and you're going to use the temperature that you calculated in Kelvin and solve for R. So you're going to get a value for R, and then you know how on the last part, calculate the percent error and discuss the accuracy of the student's gas constant when compared to the literature value. So we know the literature value is 0.08206, and so you're going to have that as the literature value. And so remember our equation for percent error. We use experimental value minus literature value divided by literature value times 100%. And percent error has to do with accuracy. The smaller the percent error, the more accurate the result. So once you get a value for that, you can discuss what you think the accuracy of the student's gas constant is. And that concludes this pre-lab discussion.